morning, friends. We have so far developed equations of motion, and we have expressed equation of motion in body fixed axis system. And if you recall, we have u dot, v dot, w dot, p dot, q dot, r dot equations. And you all know why we are developing these equations of motion. We are very focused. We are developing these equation motions to study the dynamic stability of the airplane. Now, what is dynamic stability? That if a body is disturbed from its equilibrium, and if it not only has a tendency to come back to equilibrium, but also in a finite time it comes back to the equilibrium, then you say this is dynamically a stable system. Okay? So we will now use these equations and use small perturbation theory. You have already understood some part of it in the last lecture. To repeat this, that we'll be actually talking about small perturbation for a simple reason that we do not want much of a nonlinear aerodynamics to come into the picture, and we will be operating at a steady state, and we'll assume that at steady state the aerodynamic coefficient can be expanded using a linear approximation, right? So we'll be focusing towards small perturbation, and in a small perturbation there are very basic assumptions that product of two small perturbed quantities can be neglected, and you'll see as we develop we'll be using those concepts. But let's not forget, we are trying to understand the dynamic stability of the airplane and trying to develop a model to study the dynamic stability of an airplane, to evaluate dynamic stability characteristics of an airplane through its natural frequency, through its damping ratio, and time to double or time to half. All these things you will know. But to make things simpler, what we will do, we will first do dynamic stability for a longitudinal case. Perhaps in this course we will be focusing more on a longitudinal case, and in a course on advanced dynamic stability we may go for lateral directional in an explicit form. This course is the first course on dynamic stability, so we will not unnecessarily make life miserable. What we will do, we will take simple things and understand what is the approach, how to interpret, so that we can use this understanding for much complex cases. Okay. Remember that we have u dot, v dot, w dot, p dot, q dot, r dot equations, but since I am talking about longitudinal case, that means I am talking about a motion in the vertical plane. So I will be bothered about u dot, not v dot. Okay. I will not bothered about roll. I am talking about longitudinal. So it's u dot, then this is w dot, plunging, and also the pitching, right? So three equations we will take for a consideration, and one is m u dot minus vr plus wq is equal to minus mg sine theta plus fax plus ftx. I will explain all this term, and we are already knowing this. Still, I think I must explain. Let me write this equation: mw dot minus uq plus vp is equal to mw dot minus uq plus vp is equal to mg cos phi cos theta plus faz plus ftz, and the pitching equation, that is q dot, so it is Iyy q dot plus Ixx minus Izz PR plus Ixz into p square minus r square equal to ma plus mt. So these are the equations, and we are naming it as longitudinal equations of motion. Why longitudinal? We understand longitudinal means the motion is restricted to vertical plane. So it is u dot, how the speed is changing, how the plunging motion is changing, and how is the pitching motion is changing. So that is u dot, here u dot, here is w dot, and here it is q dot. Okay, and you know this phi, theta, these are all Euler angles. You are very well now. You know that there is a particular order of rotation, psi, theta, phi, to locate the orientation of the body phase axis system with respect to the Earth inertial frame of reference, right? Now here, when I have written forces along x direction or along u direction, that is FAX, A means aerodynamic forces. So FAX, I mean component of aerodynamic forces, along body fixed x-axis, right? It's very important. Similarly, FAZ is the component of aerodynamic forces along body fixed z-axis, and MA is, of course, the moment about y-axis, aerodynamic moment. And what is FTX? FTX is because of thrust. FTX, FTZ, MT, all are because of thrust. Okay, suppose this is the airplane, right? And suppose the engine is somewhere here, so it will give a thrust. Also, if CG is somewhere here, you could see it will give a moment also, right? So we are focusing more on longitudinal stability, and that is why we have picked these three equations that you understand, right? And also we understand that we will be using what we call small perturbation. We will be using small perturbation theory, which also we have fairly good idea now. Small perturbation theory. The key point is these perturbations will be introduced where? See, what we are going to do? We are trying to see the dynamic stability of the airplane. So as per the definition, we are going to disturb it at what point? At the equilibrium, that is at the steady state. So we will introduce this perturbation at the steady state. That is the catch point, and see how the perturbed quantities are behaving. So let us say we represent u, total velocity after giving perturbation, after giving a disturbance, is u1, that is the speed at steady state, plus small quantity with the perturbed quantity u. So this is perturbed velocity. Clear? So you could see that we are using that linear approximation. Similarly, we can write v will be equal to v1 plus small v, w equal to w1 plus small w. What is w1? W1 is the steady state component of total velocity along local z or body axis z direction. For example, if the airplane is moving like this, this velocity is v star, let's say, and the x-axis is here, y-axis is here, and z-axis is this, and this is alpha, then W1 is here. W1 positive is in this direction, and W1 will have a component of V along W1, along Z direction, local Z direction. Or again, if you see better way, if this is the velocity V star, and if this is the airplane, I am just exaggerating for understanding, this is the x-axis, and this is the z-axis. So what is W1? W1 is the component of V star, total velocity, along z direction at steady state. Clear? So this should be very, very clear in your mind. And now we'll go on doing very mechanical things. So UVW you have written. Similarly, you can write P equal to P1 steady state plus small p. Then Q is equal to Q1 plus small q. R equal to R1 plus small r. Then theta equal to theta 1 plus small theta. Then psi equal to psi 1 plus small psi, and phi equal to phi 1 plus small phi. All the small quantities, PQR, UVW, theta psi phi, they are to be understood as perturbed quantity. Okay. Now we'll substitute this in this equation and see how our equation of motion for perturbed case develops into. Okay. So we'll take this case now here. We'll do some little bit of adjustment. We'll write the first equation as fxa minus mg sine theta equal to m u dot plus q w minus rv. Same thing, okay? We have written this equation. Now, notice here that we have not included ftx because we understand that if you know how to handle fx mathematically, ftx will be similar. So, you can add those ftx terms the way fx has been introduced. Okay. So, we are ftx is not added, as we understand that if I add fx and I know how to handle fx, I can similarly handle ftx also. Right? I am trying to make blackboard looks little cleaner and more focus is on the understanding rather than all those mathematical manipulations. Okay. So now what is to be done? Yes, this is f(x), I can write as f(x1) plus fx. I will explain you what is it. f(az), f(az1) plus fz, and m is equal to ma1 plus m. What is this 1? Once I am writing the quantities with subscript 1, that means these are the condition at steady state. Why? That is important because after all we are giving disturbances about steady state, which is the equilibrium point for us, and these are the perturbed quantities. So what is the meaning? If I write fax total after perturbation is fax1, that is whatever force is there at steady state, plus the perturbed quantity, perturbed aerodynamic force. Okay. So we can sometime also, just to avoid confusion, we will be stressing the conventions, the signs in a manner that you feel very, very comfortable. Many books will write fx as, represent fx as fax small x, assuming that this is only for because of perturbation, only because of aerodynamic force. For example, let's see what physically what does it mean. Let's say the plane is moving like this, okay, and at a steady state it is the drag. Let us say alpha is very small. The moment I disturb it, so there is a perturbed alpha. So some component of lift also will come along x direction, additional component. So that is what is because of perturbation, right, which is to be added over and above the aerodynamic forces at steady state. And we are again taking the advantage that we are assuming everything is linear. That is why small perturbation. Okay. This is very important. That's why small perturbation license we are using. Now you see, I will just substitute here. I will write for fax, I will write f, what is written is fax1 plus fx minus mg. For sine theta, I will write sine theta 1 plus theta. Very mechanical. Don't get upset with so many terms. It is very, very simple. So u1 plus u dot plus, what will happen here? For q, I will write q1 plus small q. So I write q1 plus small q. For w, I write w1 plus small w minus r. For r, I write r1 plus small r And for V, I write V1 plus small v. Right? This is the equation when we have introduced perturbation. Meaning thereby what? The airplane was moving so that Fax was at steady state Faxa1 minus mg sine theta 1 equal to mu1 dot plus q1 w1 minus r1 v1. That was the condition. That is at steady state. All these quantities were at steady state. So it was Fx1, sine theta 1, u1, q1, w1, r1, v1. But the moment I have given disturbance, Fax1 now has become Fax1. Some perturbed force, aerodynamic force has come because of perturbation, right? So now I can expand this by applying sine and all this multiplication. And then what I do is I will put approximations. Number one, theta is small, right? Or to be, all perturbed quantities are small. Quantities are small. And then I will expand it. Okay, let me write the expansion. What I will get is, let me write for you, let me write one complete equation so that you are happy. So let me erase this part because it will take longer length of the blackboard. So I can erase this also. So theta is small, which is again perturbed quantity. And if I expand it, what I will get, you see, f ax1 plus small fx minus mg, let me write this, minus mg sine theta 1 cos theta. You should also do it. If I commit a mistake, you should be able to correct it. Cos theta 1 into sine theta. This is equal to m u1 dot plus u dot plus q1 w1 plus q1 w plus qw1 plus qw minus r1 v1 minus r1 v minus r v1 minus r v. You could check yourself. This is sine theta 1 plus theta. I have to expand sine a plus b. So I'll get those terms. Here u1 dot plus u dot. You see here q1 into w1. So this is basically at steady state. So I have to write q1. So it is q1 w1. That term is there. q1 small w is also there. So this is small w. I should write like this, small w. Okay. And then small q w1, yes, that term is there, small q w1, and then small q wq, it is there, fantastic, we are so far correct. Then minus r1 v1, yes, r1 v1, r1 small v, very correct, and then minus r capital V1, yes, minus rv. Oh, very good. We could do this wonderful expansion. Okay, very good. Now, we are assuming theta is small, so I will say sine theta is theta and cos theta is 1. Okay, so if I expand, you see sine theta 1 plus theta, which will be nothing but sine theta 1 plus theta cos theta 1. Please understand the approximation is, if this theta is small, theta 1 is not small. That is why the sine theta was here, so we have make it theta. Theta is a perturbed quantity. Okay, this you should be clear. This is a perturbed theta. Okay, and here sine theta 1, cos theta was there. So theta is small, so we have used cos theta equal to 1. So theta small means theta is a perturbed theta. Okay. So once I do this, I get this sort of a relationship. Now yourself you see. Now you see what we are doing. We are doing longitudinal perturbed equation of motion, right? And these perturbations are introduced where? At steady state. Okay. So we are trying to write at steady state whatever the condition, and that is if A x1, you have to use this equation. Oh, this should be Ax, aerodynamics force at x. So at steady state, this is f Ax1 minus mg sine theta 1, right, equal to m u1 dot plus q1 w1 minus r1 v1. So let us see what is the condition at steady state. We know at steady state f Ax1 minus mg sine theta 1 equal to m u1 dot plus q1 w1 minus r1 v1. And if I carefully see this expression where I underline this u1 dot q1 w1 r1 v1. Okay, this is actually equal to fx1 and mg sine theta 1 cos theta. So this becomes 1 because of theta being small. So this term also gets coupled with this term. So now I can say fax1 minus mg sine theta 1, fxa1 minus mg sine theta 1 is equal to m u1 dot plus q1 w minus r1 v. So I can remove this term because they are automatically taken care, they are equal, right? So if I do that, if I take out this term, what do I get? Once I know that fx1 minus mg sine theta 1 and this cos theta is one small perturbation, this term equal to this term, so this and this. So what remains here is fx, right, minus theta mg cos theta 1 is equal to m here u dot plus q w1. Could you see this? I have removed this, so let me do for you. So this gentleman goes, okay, because they are equal to this, and r1 v1 is and this. Okay, so I am erasing this. Now we are left with what? On the right hand side, m u dot q1 w, then qw1 like this. Now remember, at steady state, what is the value of q1? At steady state, at the equilibrium, it's going like a cruise. At cruise, is there any q? Is there any pitching rate? No. So this also vanishes. Correct? But can I talk same thing about this term? qw1. What is w1? W1 cannot be 0 because, need not be 0 because this airplane axis is x here, z here, and it has some angle of attack, alpha. So the component of velocity along z direction is w1 at steady state. So this will not vanish, and q is the perturbed quantity. It is there, so it will not vanish. Then we have q into w. Okay, both are perturbed quantities, small quantities. So I can say they are product of two small perturbed quantity can be neglected. So this gentleman also goes, and here you see r1 into v. When the airplane is at steady state, cruise flight, we are talking about cruise, we are giving perturbation. So about cruise there is no r, there is no yaw rate, right? So r1 is 0. So this man also goes. This goes because r1 is 0, yaw rate is 0. Similarly, rv1, you see this term. What is v1? v1 is the side slip velocity. But I am talking about a cruise, and we are talking about a motion in the vertical plane. So naturally there is no v1. So this v1 is 0. So this man also goes. And r into v is again product of two small quantities. So they also vanishes. So what is happening? What other terms? They are there for you. One is u dot, another is qw1. So I get equation fx minus theta mg cos theta 1 is equal to mu dot plus qw1. What are this theta? Theta is perturbed pitch angle or perturbed theta. Okay. So now I can write fx is equal to minus theta mg cos theta 1 is equal to m u dot plus q w1. So this is one equation of motion which is written along the x direction, body fixed x direction. We will do some more modification or more assumption so that things look pretty simple. But for all of you, I must tell you, you have to do it once and then forget it. Then you use the final equation and try to understand the physical meaning of all these terms. That is more important. Now, since I have got equation like fx minus theta mg into cos theta 1 equal to m u dot plus q w1. This is the perturbed equation of motion, longitudinal, one of those equations. And I know by now fx is the perturbed aerodynamic force along x direction, theta is the perturbed pitch angle, theta 1 is the steady state pitch angle, u dot is a perturbed acceleration, u dot, q is perturbed pitch rate, w1 is the component of velocity along z direction at steady state. Okay. Now, there is a trick we will do. If we choose stability axis, what is the stability axis? That is, you see, this is the airplane, okay? This is your x, this is the y, and this is the z. Now, relative air velocity is something coming like this, so that is why you have got alpha. So, whenever you want to find forces along x, y, z, you have to take component, right? Like this. But now, if I choose a stability axis and define it as the axis which points towards, this is the velocity vector, so the x-axis is such that, let me do it like this. This is the airplane, and this is the velocity vector. So I align my x-axis along the velocity vector at steady state. So this becomes my z. So I write zs, xs. Clear what I have done? And let's say this was the angle alpha, correct? Between the velocity vector and the x-axis. Now what I am doing, I am defining stability axis system such that this x-axis is aligned along the velocity direction. So x-axis is here. The moment I put x-axis is here, I call it xs, that is x stability axis, z is stability axis. What is the advantage? Since this is the velocity direction, the lift and drag will be perpendicular to velocity and parallel to velocity. So I am very happy. It's very easy for us to handle the aerodynamic forces. We need not take all the components every time here and there. That is the advantage of stability axis, that you point the x-axis, body fixed x-axis, in a direction which points towards the relative velocity or air velocity direction, and so that the another advantage when it is x, s, y, s, z s axis I am choosing, that is when I am choosing a stability axis system, now the velocity vector is along x-s direction, right? So there cannot be any component along z direction because they are perpendicular, right? So for stability axis system, one other advantage for computational point of view you get is W1 will be 0. Please get this point clarified. When this was the velocity vector and it was not a stability axis system, there will be a component of V along W1 or along Z, which is W1 as per our notation, the component of velocity along Z direction, body fixed Z direction. But the moment I put the axis system such a way that the x-axis is along the velocity vector direction, then this velocity cannot have any component along z direction because they are perpendicular. So automatically at a steady state, W1 will be 0. That is, W at steady state will be 0. That also simplified the equations. And if we are operating at stability axis system, then you know W1 will become 0. So this equation gets modified to, what will happen? That equation will become fx minus theta mg cos theta 1 equal to m u dot. So this is the perturbed equation of motion, perturbed equation of motion. Of course, it is along the x direction using stability axis system. Correct? This part is clear? So what are the understanding here? That x-axis is pointing towards the velocity vector, so that there is no component of velocity along z direction. So W1 is 0. So my perturbed equation of motion along x direction looks like this: fx minus theta mg cos theta 1 equal to mu dot. And please understand, theta and u, they are perturbed quantities, along with fx, which is perturbed aerodynamic force along x direction.